Welcome. Thank you to Cantina team for organizing this awesome event, and also to Certora for participating here with us. My name is Kasper. I am Solidity Dev at Euler, and I am the main person behind the EVC, the Ethereum Vault connector, and reward stream implementation. Both of those projects are in scope of this competition. I also helped a little bit on the Euler Vault kit, although here Darek probably is an expert. He will follow me here. Anyways, if you have any questions throughout the day about anything really, I will be here. We all will be here, so feel free to ask them. And my plan for today is to explain to you what is the EVC, what is the concept behind it. Probably we will not really dive into the code of the EVC because we will not have enough time. But I think that what is more important here is to understand the concept behind it and how it works really. Yeah, so if you go to the Cantina website and go to the competitions list, if it works. Sorry. Okay. Anyways. It seems like my internet doesn't work. Okay, here it is. Yeah, you will find our competition, and here in the documentation section, you will find the links, and this is the website that I will be referring to throughout this presentation. So the EVC.WTF is like a main reference point for the EVC. Sorry. No, my mobile internet works better. The EVC.WTF is the main reference point website for the EVC. And here is where you will find all the information about it, full descriptions, also the white paper that is being pulled here directly from the repo. And yeah, so what is the EVC? The EVC is a smart contract which is meant to connect vaults and let them use one another as collateral. And this is the main reason why we build it. So probably you are all familiar with what the vaults are, and these are the main primitives out there in DeFi, which basically allow people to deposit their assets, typically get some share tokens that later on can be redeemed from the smart contract. But typically what the vaults do is they take those users' assets and they implement some active strategy. They redeposit those assets into other smart contracts in order to generate yield. But we took a step back and we thought that maybe it would be cool to take the most popular standard out there for the tokenized vault, which is ERC 4626. And maybe it would be cool to add borrowing functionality directly to the vault. Of course, it's not easy because, as you know, the vaults are standalone smart contracts and they don't really know anything about each other. So it wouldn't be safe to simply allow users to borrow from a vault. And this is because those vaults have no way to really enforce collateralization, right? So user could simply take a loan and run away with the assets. It would instantly create a bad debt. So in order to enable vaults, in order to enable borrowing functionality for the vaults and in order to let them use one another as collateral, you need this additional missing piece, which is the EVC. And what the problem that the EVC solves is the lack of coordination between the vaults, and also it mediates between them. So basically, the EVC is responsible for triggering the account status checks whenever any smart contract, but typically a vault, signals that such a check has to be performed. And it's up to the EVC to decide when those checks should happen. And also, the EVC allows the vaults to seize collateral in case liquidation is needed, right? So if the prices change, if the debt of the user grows, typically we will face a liquidation scenario. And the EVC is there to mediate between the vaults and allow them, allow one vault, the vault from which user borrowed, to seize collateral from the other vault, which was enabled as a collateral. And what we hope with the EVC is that it will become this base layer, base protocol on which other builders, not only us, but also others can build their own cool protocols, like other lending protocols, really. Stable coins, synthetics, yield aggregators, margin trading apps, and many more. So how does the EVC work? I will use a diagram here. So typically what happens is that user deposits some assets into a vault. So basically they call a deposit function on a vault that they want to use as collateral, right? This is a typical interaction, but what is very important is that the user needs to notify the EVC about which vault they intend to use as collateral and from which vault they intend to borrow. This other operation here, enable collateral, is just that. So by calling this function, the user notifies the EVC that they will want to borrow from a given vault, and they enable this vault as a controller because from that point on, this contract will have power to seize any assets that user deposited in the collateral vaults that they have enabled. So this is very significant action, and only trusted controllers should be enabled by a user. When that's done, what happens is that the user lets the EVC know which vault they intend to use as a collateral, which vault they intend to use as a controller. They deposit the assets. And when user is depositing the assets, there is no need to check the account status, and this is just because the deposit operation can only increase the health score of the user. However, when user borrows, what happens is the vault from which user borrows needs to call the EVC in order to ensure that the user has really enabled this vault as a controller, so that it's safe to yield the assets to that user, because this vault will be in control. Then the typical borrowing logic will be implemented, and then, very important thing, at the end, that vault will require account status check on the EVC. And then it is up to the EVC to decide when that check should happen. If we have a direct interaction with a vault, so when a user calls a borrow function directly on the vault, such a check would typically be triggered right away, right? So the EVC gets the signal, and the EVC calls back to the controller in order for that controller to determine if the account is healthy or not. If it's not healthy, then such an operation would be simply reverted. There are two types of checks that a vault can use. There is an account status check, which is the one that checks if the account is healthy, and there is the other vault status check, which can be used to check if the vault itself is healthy. So for example, this is a check that can verify if supply or borrow caps were not exceeded during a given operation. And this is also a type of check that was scheduled here when user was depositing. Simply here, the vault could check if the supply cap was not exceeded in that operation. What is very important is the fact that whenever the EVC triggers the account status check, it always calls back into the controller vault. So it means that if user did not enable any vault as a controller, it means that they have no borrow position. So the user account will be considered, the user account status will be considered valid right away because there is no borrow. However, if there is any borrow position, it will be the active controller that will be called in order to determine if that borrow position is still healthy and that the operation can succeed. That leads us to very important fact that the user can have only one controller enabled at a time. And this is how we enforce only one borrow per account. User can have no more than one active borrow position for their account. However, this is mitigated on the EVC. I will explain you in a bit how. However, thanks to the fact that given user can have only one borrow position, it's much easier to coordinate because that's how we know that all the collaterals enabled for an account they support this one borrow, right? And all the positions they are isolated from each other. So this is very important. When users withdraw their assets, the flow is a little bit different. So basically, not only when they withdraw, but basically when they do anything that may deteriorate the health of the account. If such an operation, let's say that this operation is simple withdrawal, is called on a vault, that vault will also, after executing that operation, it will also require the account status check. And it will notify the EVC, hey EVC, please perform the check on this account because its health might have deteriorated, right? And what the EVC does is it checks the account status check, but this time, considering that it's withdrawal from not a controller vault, but for example, withdrawal from a collateral vault, the EVC will not call back into the vault that requested the account status check, but it will call back into the controller vault if it's enabled. If it's not enabled, it means that user has no borrow. If it's enabled, it means that user might have a borrow, and this controller vault will get called, and it will determine if, considering whatever has just happened, that withdrawal, for example, if this account is still healthy, right? Considering that user withdrew some assets from a vault. And if this check passes, only then the operation will succeed. If not, it will revert. The EVC implements many more features to increase the user experience. And you can think of the EVC as a glorified multi-call contract, but also a contract that is an alternate entry point for calling the vaults and also other contracts. So basically, the EVC is responsible for the authentication of the caller, and then any vault or any smart contracts that integrate with the EVC, they can rely on the fact that the caller of the EVC was authenticated, and therefore, whatever the operation is, it can be performed safely. So the contract will rely on the address that was authenticated by the EVC. And the way it works is that maybe a better example will be a batch function. That is one of the flagship features of the EVC. So the batch operation allows the user to execute an array of different operations that are touching different vaults, different smart contracts, different accounts. And what the user does is it calls the batch function on the EVC, providing the list of operations that they want to execute. Those operations will get executed in a loop. All the checks will be scheduled throughout that loop execution. So each vault, each smart contract will request the account status checks, vault status checks, whatever they need. And only then, after that loop is executed, only then the control will be given back to the EVC in order to perform those checks. But what is very important here is the fact that when the user calls the EVC, it is the EVC responsibility to authenticate the caller, that this user is really authorized to perform whatever operations are contained in this batch, right? And the EVC does it, and then whenever the vault is called, they use this get current on behalf of account function in order to get the address of the authenticated user, basically get the address of the account on which this operation is being executed, right? And thanks to that, we can provide this higher level of abstraction when it comes to the caller of the contract. And it enables batching, it enables the deferred status checks, because as I mentioned, the loop will be executed and those account and vault status checks will be scheduled, but they will only get executed at the very end after this, this loop ends, right? Which means that transiently, throughout the batch, some checks, some invariants might be violated. So for example, user can borrow something without providing a collateral, but as long as when the checks are being performed, that violation is solved, such an operation will succeed. And also, it's very gas efficient because the checks will get executed only once for each account and for each vault for which they were scheduled. So when we get finally there, the EVC will loop over all the accounts for which the checks were scheduled, and it will loop over all the vaults for which the checks were scheduled respectively, and it will perform those checks by calling into either either into controller vaults of the accounts or into the vaults that schedule the vault status checks for themselves. But also, thanks to the fact that the EVC is an alternate entry point to the smart contract and it performs the authentication of the caller, we can abstract everything further. So what we can do is we can enable sub-accounts on the EVC, which means that each user on the EVC, each Ethereum address on the EVC, out of the box gets 256 sub-accounts for them. And thanks to that, we can mitigate this limitation of one liability per user, because in fact it's just one liability per account, right? But considering that the user has 256 accounts, from one Ethereum address, user can have 256 borrow positions. However, in order to use the sub-accounts, the vault needs to be called through the EVC. So basically, the user will call the EVC and say, hey, I want to borrow using my sub-account, right? The EVC will check if that whoever is calling it really can perform this operation for this sub-account, meaning that the EVC will check if it's the owner of the sub-account calling. And if that's the case, only then the EVC will allow the vault contract to be called, and then the vault contract will rely on the account that was authenticated by the EVC. So when the vault calls this function, it will get the sub-account address, not the real owner address. Also, another feature that is enabled by the EVC authentication are operators. And you can think of the operators as, for example, account or position managers. So the EVC allows users to install an operator, which is any Ethereum address. It might be a limited smart contract, and typically it will be a limited smart contract, which can only perform a subset of operations. But in fact, it can also be EOA, if user trusts that EOA. And when user enables an operator, that operator can also call the EVC and act on behalf of some other address that enabled it, that authorized it. So the way it works is very similar to how the sub-accounts work. So when whatever caller is calling the EVC, saying that they want to perform some operation on behalf of some other account, the EVC will first check if it's a sub-account of this caller, and if not, it will check if it's an authenticated operator, maybe. And if it is, such an operation will proceed. And finally, the most important thing that is enabled thanks to the fact that the authentication is delegated to the EVC is the liquidation flow. So as I told you at the beginning, the EVC mediates between the vaults in order to allow the controller vault to seize collateral from a user in violation if there is a need to do so. And the way it is performed is, this is a whole liquidation flow, by the way. The way it is performed is that the liquidator typically calls liquidate function on a controller vault, which means on a vault from which user has borrowed. And after all the safety checks are executed, the liability vault will use the control collateral function on the EVC. And basically it will call into the EVC, instructing the EVC that they want to call into a collateral vault for a given violator address, and they want to perform some operation, for example, transfer of shares. And then it's once again the EVC responsibility to authenticate the caller. So the EVC will check, okay, so this guy is calling the control collateral function. Is it really enabled controller for this violator account? If it is the collateral vault that the controller wants to call really an enabled collateral vault? And if that's the case, only then the EVC will allow this operation to proceed. And the EVC will call the requested transfer function, in this case, on the controller vault. And the controller vault would not even know that the liquidation is happening, right? It will simply see that, okay, EVC is calling me, so I will just get the address that was authenticated by the EVC. In this case, it would be the violator address, and such an operation would proceed as usual, right? So from the collateral vault perspective, it doesn't even know that the liquidation is in progress. It will simply require the account status check as usual, because when shares are transferred, the health of the account might get deteriorated. So this vault will require an account status check on the violator. It will require the vault status check for itself, right? The control will be back to the controller vault. It will finalize the liquidation. And very important thing that will happen is that if the vault is considered trusted, and it must be considered trusted in order to become a collateral vault on the controller. The controller vault will forgive the account status for the violator, the one that was scheduled here, because we know that this account is unhealthy. That's why the liquidation happens in the first place. But sometimes the liquidation does not bring the user back to full health, and that's why we need to forgive this account status check in a safe manner. If you want to read a little bit more about it, we have lengthy explanations in the documentation itself. But the important fact is that the controller will forgive the account status check, because it knows that in the end it will be this contract which will perform this account status check, so it can be safely forgiven here. The liquidation will conclude, and only then the account status check will be performed on the liquidator itself, because the liquidator must be healthy after the liquidation, and we will also perform the vault status checks in order to check that none of the vault invariants was violated in that process. The last cool feature that I would like to mention for the EVC is the permit. And the permit is just an alternate entry point to the EVC, which allows a user to sign EIP 712 data message and sign it and allow somebody else to execute that payload on their behalf, provided that that caller, holds a valid signature of a user. And you can use that to, for example, implement stuff like pending orders. So that payload can encode, for example, some kind of a condition that, for example, this payload can only be executed when the price drops to X, and only then it will be able the caller will be able to execute it successfully. And with that scheme, you can implement, for example, pending orders, gasless transactions, but also intents. I think that this would be it. Maybe one more important thing to mention. There is some scheme that we use in the EVK, and we encourage everyone to use it. It's not strictly required, but we thought that this is pretty nice way to do things. So even when the contract or a vault is being called directly, what we do is we use the EVC call function, and call function is like a batch, but batch of one batch item. Simply, you don't need to provide an array. You put the call parameters directly, and we use this call function in a callback manner in order for the EVC to defer the checks for us. And by doing this, we can unify the workflow in the vault or in a smart contract, because we know that by doing this, right away we are in the deferred checks context. So we know that the execution is being controlled by the EVC, and we can right away rely on the get current on behalf of account status function, because the authentication flow is also unified. So what happens is that when user calls an operation on a vault, we encode that operation in a call to the EVC. The EVC sets its context so that this address can later on be retrieved, and it calls back into the vault using the same operation, using the same message data as the user originally used. And by doing this, at this point, the vault will detect that it's being called by the EVC, and if it's called by the EVC, it can assume that the checks are being deferred, and that it can use this function in order to authorize the user. And then the flow proceeds as usual. Yeah. So I think that I set the ground for Darek, and Darek will explain to you how the EVK works. Probably he will dive into the code. But I thought that it's very important for you to understand how the EVC works, because the EVK is a client of the EVC. So it will be just easier to understand whatever Darek is talking about. Okay, this is it. Yeah, I mean, if we have enough time, we can do questions. Okay, cool. Okay, do you have any questions?
I have one very simple question.
Yep.
Clearly there's some overlap between the permit system and the operator system.
Mm-hmm.
Talk about the design intent, the use cases, where you think one would be appropriate than the other, and kind of what you're thinking in that system.
Okay, so for example, with the operators, what you can do, you can write a smart contract which can perform like limited set of operations. Like for example, with operators, you can implement stop losses or trailing, basically conditional orders, right? And you can put the contract out there, and you can have a bot keeper network, and you can allow anyone, if given condition is met, to, for example, close out your position, right? And for the permit, by definition, if you sign something, it does not become public right away. So yes, you can publish it and let that signature to be discovered and let anyone to call the permit function on the EVC using your signature. But you can also give that signature safely, secretly to your relayer, to someone trusted, and only that person will be able to execute an operation on your behalf. So there is some overlap, but not fully. Like if you enable an operator, it's public right away. If you sign a signature, it might be, but doesn't have to. Depends on what you want to achieve, really. And also permits enable gasless transactions right away.
I think in one of the examples they had, like, you sign a batch which has some checks in the batch saying, are these things, are these conditions met, otherwise revert it. So I think this is also a method of implementing certain things like stop losses.
Yes, but it's more limited because that payload is static, right? Whatever you sign is static. And that's why some workflows might be harder to achieve using such a permit, right?